Hello everyone. Welcome to the first lecture of Power Electronics. So let me add the title Power Electronics. It's in your semester 5 course, and today's date is 17/8/2022. Yeah. So let me at the outset tell you all that there are two broader categories in this Power Electronic course. First is we will be investigating about power converter circuits. Power converter circuits. And second broad category is about power semiconductor devices. Power semiconductor devices. You all have studied semiconductor devices in your lower semester, uh, which was which were diode, BJT, MOSFET, JFET, right? But in this semester, we'll be dealing with some power semiconductor devices. So some of the power semiconductor devices are SCR, then we have DIAC, TRIAC, then we have IGBT, then power MOSFET, and finally power BJT. Power, okay, sorry for this, power BJT. So these are the various power semiconductor devices which we are going to study. And related to these devices, we are going to broadly focus on their operating principle, their construction wise they are different than semiconductor devices because they have to handle large current and voltage capabilities, and then their IV characteristics. Okay, sorry for this. Their IV characteristics, then their ratings, which will be available in the data sheet if you check any power semiconductor device, and finally their applications. So each of them have a unique set of applications wherein they will be useful. Okay, fine. So this was about power semiconductor devices. Now these power semiconductor devices, actually there is one more which I have not added over here, which is power diode. So we'll briefly also cover power diode because without diodes, the topic of rectifiers is incomplete. So we'll also touch upon power diode. So this entire power semiconductor devices will comprise of module number 1. So this entire thing will go to module number 1 in your syllabus. Okay? Module number 1. Okay. Next, we go to power converter devices. So basically here we'll be studying about the various types of power converter devices. So first of all, we'll categorize into various types of power converter circuits. So the first type is AC to DC. So basically we can call it as AC to DC converter. Second type is DC to DC, DC to DC converter. The third type will be DC to AC converter, And finally, we have AC to AC converter. Fine. So these all are converters. Fine. There are four types. So each of these four types, like for example, AC to DC, there is one complete module based on that. So AC to DC is called as rectifier, right? DC to DC is called as chopper. DC to AC is called as inverter, and AC to AC converter is named as AC to AC converter itself. Fine. Now, mainly our focus of attention in power semiconductor devices, the most focused device will be SCR. So, in addition to these things, we'll also focus on the turn on mechanisms of SCR. So, how to turn on SCR? So, we have to worry about it. Turning, turn on techniques, and also we have to look upon, it's very difficult to turn off an SCR, but it's possible. So we'll look at various commutation circuits which are called as turn off circuits for the SCR, right? So we'll focus on how to turn on a SCR, what are the different techniques, and how to turn off the SCR, which is very, very important in the case of power converter circuits, right? And also we'll talk about SCR protection. How do we protect such a high current, high voltage rated device? So we'll also talk about SCR protection techniques. Sorry for this. Yeah. So now let's proceed further. I hope this is not overlapping. Yeah. So let's proceed further. And let's just for a few minutes talk about AC to DC conversion. Okay. So let me add this topic over here, AC to DC. And this is called as rectifier. So you all have studied rectifiers in your lower semester, right? So why we have been studying this device again? I mean this circuit again. We will be investigating it further. Before answering this question, why rectifiers in power electronics? Let us understand how well you know about AC and DC quantities. So I'm going to draw a few waveforms. You have to let me know whether they are AC or DC. Okay, this pen is behaving a little weird today. Apologies for that. Okay, so I'm going to draw three different diagrams, and you have to let me know which one is DC, which one is AC. So first one is this, second diagram is this, and the third is this. Let me redraw it properly. Okay, these are all versus time, and these are all quantities. So let me mark it as this is 1, 2, and 3. So I'll give you a few seconds to think upon and let me know out of these 1, 2, and 3, which ones are DC quantities. Which of the output is DC quantity? Which of the waveforms is DC? Okay, I'll wait. Yes, rightly said by one of y'all that the first one is a DC quantity. There is no questions asked in this. The value of the voltage is fairly constant over here throughout. So it's a DC quantity. What about the second one? Well, it looks appears to be a AC signal, but it's not, right? This also looks like same, right? So what is the difference between 2 and 3? Anyone? Yes. Waveform 2 is again a DC. I'll let you know. And waveform 3 is a AC. Now, how did I make this distinction? So remember, uh, waveform number 3, which is marked as 3, is a periodic sinusoidal waveform. It's a AC quantity, right? So how it is a AC quantity? So what is the mathematical definition of AC signal, periodic AC signal? Uh, its average value should be equal to 0. Then we can call it as a periodic AC signal. So then we can call it as a periodic AC signal. So this definition is satisfied over here. So it's a AC quantity. Now over here, it's not. Correct. Now let me give you example over here. Let's me focus over here. So let me expand this part of the waveform. So let's say that the amplitude over here is 10 volts and here it is minus 10. And here we have one time period, correct? From year to year, one time period. Fine. So over here the waveform starts from 0, it goes to 10, again it goes to 0, then it goes to 0 to minus 10, then minus 10 to 0, right? So at the end of one cycle, its average value is coming out to be 0. So any AC periodic waveform whose average value is 0 is a AC, pure AC signal. Fine. Now let us look at this example. So let me just draw a center line over here and let me just call this voltage as 10 volt. This voltage will be, let's say, 15 volt. Sorry for this again. And this voltage over here is, let's say, 5 volt. Now can anyone tell me what will be the average value of this waveform? What's the average value of this waveform? Yes, rightly said, it's 10 volt. Now why it is a 10 volt? Because if you see, the waveform is starting at 10, moving towards 15, again from 15 to 10, and then from 10 to 5, and then from 5 to 0, 5 to 10 volts again, right? So basically your 10 volts is the average value of this signal. So this we can call it as a positive average. This is a plus 10, right? So the average, we have a positive DC output, correct? Average value of the waveform is positive, right? So that's how we distinguish between AC and DC signals, right? So yeah, we can have another waveform with whose waveform looks like this. We can have a negative average value also. So let's say your waveform is starting from here. So this kind of a waveform will have a negative average value, but it's non-zero. So again, this is again a DC signal, okay, with a AC ripple. Fine. Okay. So now that you have understood about the AC and the DC quantities, let us look into more details, right? So let's just consider 230 volts AC mains. All your sockets at your home, which runs the home appliances, are all 230 AC main signal, and it's 50 hertz. Now the question is this a RMS value or it's a peak value? Is this a RMS value or a peak value? Sorry for this. Yeah. Is this RMS or peak? Yes, it's RMS. This is correct. It is 230 AC mains 50 hertz RMS value. It's always RMS value. But when we view such a AC signal on a CRO, we have to measure it in terms of peak value, right? So let me show you, a small example of it. So let's just consider this is our AC main supply. Okay, this is your V in, let's say. So this is, let's say, your V in. Okay, so can I mark this as 230? This peak and this peak as minus 230? No, it's wrong. Because over here we represent the plus Vm and minus Vm, the positive peak and the negative peak. So there should be a relation to convert a peak value to RMS value. So peak value is root 2 times V RMS value. It's a very, very important relation. Please note it down in your books. So peak value is root 2 times V RMS value. In our case, what is the RMS value given to us? 230. So 230 into root 2 will be, just calculate in your calculators. What's the answer it is giving? The peak value of your input signal will be root 2 into 230, and that comes out to be 325.269. So we can approximate it to 27. So this is my peak value of the input signal. So this I have to write over here. So this is 325 point, this will be 325.27 volt, and this will be minus 325.27 volt. Okay, so this is the positive and a negative peak value. I hope you're following. Now who is going to tell me how much is the period of this signal? How much is the period of this periodic AC signal? This periodic average value of this signal will be 0, correct? Because it's a periodic signal, and about 0, and its average value is 0 after one period. So how much is T? So remember, the frequency is around 50 hertz. The frequency of the signal is around 50 hertz. So your time period will be 1 upon 50, and that will come out to be 20 millisecond. That means from year to year we have 20 millisecond. Fine. I hope it is very, very clear to you. What are the concepts we have learned today? We have learned about how to identify a AC quantity and a DC signal and a DC quantity, right? So whose average value of the waveform is 0, that is a periodic pure AC signal, and whose average value is non-zero, that means it can be positive or it can be negative, that's a DC quantity with the AC ripple present in it, right? And the circuit which converts AC to DC is called as a rectifier, right? Now let's come back to rectifier. Why study rectifiers in power electronic devices, right? So before that, let me give you one small check of one more small waveform, and let me know whether it's AC or DC. So one more example. So this will be one of the outputs which you will be getting. Okay, sorry for this again. Okay, so yeah, I'll give you some time. Oh, very well. Yes, it's a DC signal. Absolutely correct. It's a DC signal. How? And how? What is it? What about its average value? Yes, its average value is negative. How do you identify it? You see, the majority of the person is negative. So the average value of this signal will be, it's repetitive, correct? But its average value is negative. Correct. Yeah. So this makes sure that you have understood the difference between AC and DC quantities. Now, why study rectifiers in power electronics? Fine. So basically, the rectifiers, as we know, it involves, in your lower semester you have studied diode-based rectifiers, where you have used a lot of diodes and transformers to step down the voltage from 230 volts AC mains, right? So you have studied diode-based rectifiers. Now these diode-based rectifiers, they cannot be controlled. Okay, so these are categorized into uncontrolled category. So these are called as uncontrolled rectifiers, right? So we have no control whether the diode, when it turns on, and when it turns off, right? It just turns on when the condition is met. Now, in this semester in power electronics, we are going to study SCR based rectifiers. Correct. Even the name SCR stands for silicon controlled rectifier. Okay. So majority of the SCR applications is in rectifier. Correct. It's also used for other conversion, but most famous is rectifier circuits. So in SCR based rectifiers, what's the special thing over here which differentiates it from diode rectifiers, apart from the large power and the voltage and the current ratings? they are called as controlled rectifiers. That means it depends upon the designer when this SCR will turn on, and it even, I know it's difficult to turn off an SCR, but also it can be controlled, right? I mean, it's really difficult to control the turn off time, but at least the turn on time can be, I mean, the turning on of SCR can be controlled with relatively ease based on SCR. So SCR based rectifiers are controlled rectifiers. So in next few lectures, we'll be discussing about this controlled rectifiers, and then this tag about controlled rectifiers will be more clear then. Okay. So yeah, so we have come to the end of the lecture. Next time we'll start with power diodes, ideal characteristics, and then we'll jump on to the SCR ideal characteristics, and then we'll move on to the rectifier topic. Correct. So before I conclude for today, these four topics which I marked over here, let me circle them with a different color. These four categories in itself forms one complete module in your syllabus. Okay. So this will consist of module 2 to 5. Okay. So this is in short your syllabus for your power electronics, right? So we have two categories over here: power semiconductor devices, which will which will be covered in module number 1, and module number 2 to 5. We have various power converter circuits, which is AC to DC rectifiers, DC to DC chopper circuits, DC to AC inverter circuits, and AC to AC converters, right? So this is in short a short intro on power electronic syllabus. So that's it for today. Next time we'll directly start with your actual syllabus topic. So thank you for joining.